Okay, so we want to talk today about one-dimensional kinematics. Now, a lot of you've had high school physics, and when I say one-dimensional kinematics, you might think of this equation. Whoops, I got two screens going here. Sorry about that. So when I say one-dimensional motion or one-dimensional kinematics, a lot of you probably think about the equation delta x equals 1/2 a sub x t squared plus v initial x times time. Okay, cool. This is for constant acceleration. And there are some other equations that are associated with that. And then what do these terms mean? All right, so delta x, does anyone recall what delta x means in this equation?
Change in position.
Okay, yeah, it's a change in position. Okay, so change in position, that's one good way to say it. There's another term for that. Somebody else. Does anybody know the other term for change in position? It starts with D.
Displacement.
Displacement. And I'm going to underline the P. I'm just going to write displacement like that. Sorry, I ran out of room. Now, one of the things here that I want to know, and maybe you remember this, maybe you don't, is displacement a scalar or a vector? Does it have size? That would be a scalar. Or does it have size and direction? What do you think?
It's a vector.
It's a vector, right?
It's a vector. And this is one of the things that's very frustrating to students in this chapter. We don't really see the vector written. Strictly speaking, this should be a vector right here, here, and here. This is an acceleration vector, right? You could accelerate to the right, or you could accelerate to the left. Similarly, you could be moving, have a velocity to the right or to the left. And so, strictly speaking, there's a vector on here. However, when we're in one-dimensional motion, we can make our life a lot simple by thinking, well, if this is a vector, usually we would say something like delta x, whoops, sorry. Let me rewrite the same equation down here in a different style. And there are different ways you might write this one. You might write x final minus x initial. That's the same basic equation. Now, the idea here is if we're just moving in one-dimensional motion, I could literally stick an I hat on everything here. And by that, I mean the change in position to the right. And this would be the acceleration to the right. And this could be a positive or a negative number. This could be a positive or a negative. Same thing with this velocity. And then, of course, since most of us are lazy and the first thing you do when you have an equation is cancel out anything you don't need, the first thing we cancel out is usually this I hat, which gets us back to the original equation up here I had like this. So my reason for pointing this out is when we're doing constant acceleration kinematics, we typically do not write the vectors, but you're supposed to know it's a vector. Okay. And most of you had a high school physics class where you did a lot of word problems with this. If you had physics 110, that's basically the equivalent. We did a bunch of word problems with these equations. So that's cool. All right. So I'm going to pause here in just a second. I'm going to just summarize this like this. We say that we might have constant acceleration equations. So if we have a constant acceleration problem with 1D kinematics, we're going to use our standard equations. And there are special situations that apply for free fall, which is AY equals negative G, but it's essentially the same type of problem. If you have a constant acceleration problem, we're going to use this delta X equation, the V final X equation, and the V final X squared equation. And I'll just put blah, 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 blah. We can look those up. All right. So that's one style of problem. What if A is not constant? There we can run into some challenges, but I think maybe this is a good summary of that. And I'm trying to give you a summary up front just to motivate what we're going to do in this chapter. By definition, now we could use calculus in this class, whereas we couldn't in maybe your high school physics class or perhaps in physics 110. I don't know how much calculus you've used, but now calculus, you know derivatives because that was a prereq for this course. So we usually say the acceleration is the derivative with respect to time of what? What do we take the derivative of to get acceleration?
The velocity?
Velocity. And those are both vectors. Now, again, we could do this the same way as before, where we say this is something like a sub x equals d dt of v sub x. And then, just like before, we could put our I hats on there again and cancel them out. And so sometimes you'll see this written like this, where this is actually the x vector and it's of acceleration. And this would be the x vector of velocity. And we just kind of ignore the I hats. So sometimes in this chapter, we're going to be lazy and ignore the I hats or the vector arrows. That doesn't mean they're not vectors. All right. Now in practice, this is all well and good, but how do we use this? Well, in the way we typically use this is we actually rewrite this. So let me scroll down here a bit. One of the things we could do is rearrange this like this. And actually, I'm going to get lazy and stop writing the arrows here. So, but I will put a subscript x just so we have it here. So all I did was I cross multiplied by dt. If you're wondering if that's mathematically legal, it is, as long as these are differentials, okay? So now in this case, this is related to a derivative. What is the opposite action? Okay, so if taking the derivative is the action, what would be the inverse of that?
Antiderivative?
Antiderivative, or the
Integral.
integral. So what we could do here is integrate this. We have to be careful, though. This only works if the acceleration is an acceleration as a function of time. Okay, so in this case, this equation will work if the sorry for that glare, I'm trying my best, people. So this trick will work if the acceleration is a function of time. Okay, so, and then if we get this, all right, this is one method you could use here, and I'm kind of running out of space here, but I'm trying to give you the big picture. We're going to go through the details in a minute. So let's point this out. Just to summarize this, we could say a sub x equals, dv dt takes us to the integral of dv is the integral of a dt if a equals a as a function of time. All right. Gosh, glare. There we go. The next step would be velocity in the x direction is dx dt. So what would be the equivalent phrase here? The integral of what? So when we looked up here, I took this equation and I rewrote it as this integral. What would this integral be?
The integral of dx?
Integral of dx, and this should equal
Vx times dt.
Vx dt. Thank you. And I did drop an X up there. What is the special condition here? We had a special condition before right here. What do you think the equivalent special condition would be?
If Vx is a function of time.
Yep. So basically, if we have polynomials or things like oscillations where we have sine omega t or exponential decay e to the negative alpha t, these are the kinds of things we can straight up integrate. Okay. Okay. And so this is kind of the summary of a lot of problems, about 2/3 of the problems in the chapter. We're either going to have, sorry, let me scroll up just a little bit here. Move this back just a hair. If you have constant acceleration, we're going to try and use standard equations. And even if the acceleration is constant at this value for part of the problem, then constant at this value for another part of the problem, we can handle that. So basically, as long as you can cut something up into stages, we could use this upper situation for constant acceleration. If we have non-constant acceleration, where we have some crazy function as a function of time, what we could do is we could take that acceleration and integrate it to get the velocity. From there, we could take this velocity and integrate it again to get the position. All right. And then just so this is all on one sheet. All right, I'm running out of room here. There's a last piece. For this chapter, the last piece is understanding xt, vt, and at plots. So basically, it's not enough. Sorry, let me adjust it just slightly. There, we got it all on one sheet there. So this is the goal of chapter 2, and it's pretty hefty. So in Physics 110 or your high school physics, you mainly focused on this part. Maybe you did an occasional one like this. And there's actually in our notes, we actually can go even further, and I could tell you what do you do if this is not true? Well, that's called Math 184. But yeah, so there's a whole class in your math department. If you're wondering, what do we do if it's not a function of time? And you might be saying, all right, well, the classic example where acceleration is not a function of time is air resistance. Air resistance depends on the speed. Think about it. If you put your hand outside of the window of a moving car, the air resistance depends on how fast you go. Well, if the force depends on the velocity, so will the acceleration. How would you handle that? Well, we'll discuss that more later as time permits. Okay, so this is the big picture. Before I go on and start breaking this down and doing sub-steps, I want to see if there's any questions from you all. Let me go to gallery mode just in case. Okay. All right, that's just to motivate us. You could chime in at any time. You can throw it in the chat. You could do whatever. All right, let's go back to speaker view. All right, so all right, so from here, let's take a look. Let's do a screen share of the workbook. Let's go to, shoot, which one do I want to do? Whoops, where is it? There we go. All right, so are you seeing my screen right now? Oh, whoops. I just got a second monitor over the weekend and tried setting that up. And so I got to try a different screen. Sorry about that. We want to do screen 2. There we go. Sorry about that. Now you can hopefully see this stuff. All right, so on page 21 of the workbook, you can see that there's a bunch of definitions here. And so I'm going to let you kind of keep this in mind. If I'm talking in class and you forget something, you may want to look at these definitions here. All right. And so these are all the symbols that we've got in case we need that when we start to work problems. All right. So there's that. Let me clear all my drawings and scroll down. All right. Here is some of the review for what I was just saying here. Oh, I forgot to mention this, moving forwards and moving backwards. Typically, we assume, I guess this seems obvious to me, but I should clarify. Moving forward, usually I mean plus I hat or plus j hat, basically in the positive direction. Now, one of the things that's confusing for students is the words moving, right? Moving is not acceleration. Moving talks about velocity. The combination of velocity and acceleration. So if I go like this, if I look at both of these things, the combination of velocity and acceleration relate to speeding up or slowing down, things like that. So more on that in a minute. I'll just point this one out. Look at this right here. Some students find this confusing at first. If your velocity is negative and your acceleration is negative, you are not slowing down. If you're moving to the left and you accelerate to the left, you should speed up. So sometimes students need to be reminded of these two. I think it makes sense once you hear it out loud and say it, but that's what these last two lines mean. Most people have no trouble thinking, oh, if acceleration is positive, you're probably speeding up. However, if acceleration is positive to the right and your velocity is negative, you're actually slowing down. So the point is, a positive acceleration by itself is not enough to tell you if you're speeding up or slowing down. It's the relative signs of acceleration and velocity. More on that soon. Here's a warning I give. Be careful when an object reverses direction. When an object reverses direction, it's changing from moving one way to moving another way. So it's either going from a positive velocity to a negative velocity, or so let me just draw a little animation of that right here. Imagine some objects going this way and then it turns around. Well, right at the spot where it turns around, up here, velocity was this way. Down here, velocity is that way. The turnaround point has velocity equals 0. So this is a very useful thing to just keep in the back of your mind. Remember, at turnaround points, velocity is 0. However, not necessarily the acceleration. All right, somebody's trying to get in here. Let me add them in. Whoa, where did it go? All right, let me get Cesar in here. Okay, sorry about that. And then here are the classic equations that are also on the back of your book. Some things I might want to point out here. If you're using these equations, there's different ways to write them. Sometimes you write them with delta x. Sometimes you write them with x final minus x initial. Now, keep in mind, if we have x final minus x initial, all I did was I just brought this x initial to the other side. And so when you see these equations, you might see that all over the place. Also, notice sometimes, I don't mean to change notations on you, but this is the initial velocity in the x direction. This would be the velocity at time 0. That's also the initial velocity. Similarly here, sometimes people get lazy and they interchange final velocity and just Vx. So they say the initial, you give a subscript, and then the final, you don't give a subscript. So depending what book you use, what high school class you had, who you had for Physics 110, different teachers say this different ways. Just be aware. And again, these equations are valid for constant acceleration. All right, so because a lot of us have done that already, I might come back to this after I talk about the non-constant. So let me scroll down here. I'm going to try and do things a little bit different way here. There's lots of example problems here, so you could look at these. And I want to point out something else too as I'm going through this. Here's where I start to talk about free fall and the y direction. So this is on about page 27. I talk about the y direction, and I give you a big problem here where I talk about the y direction. 2.13, I think, is required for you. So you can have your solutions open and really see some good examples there. And then there's some more. We'll come back to those later. All right. So there's a whole bunch of practice problems. Here's a section that talks about the graphing, page 31. I'm going to, again, skip over this because we've talked about it in other classes, and you've probably seen it in high school or in calculus, but I will come back to this, all right? So I'm going to come back to this. There's lots of good questions in here. I love graphing questions. All right, where are we? Sorry, this is taking so long. Somewhere right around in here. Oh, shoot, I just passed it. And then, okay, so this is where I wanted to pick up. All right. And so this is the calculus part that I was talking about here. So this is page 42 in the workbook, if you're looking at it, right? And so what I want to do is I want to use these equations and explain how I got them and then apply them to the example problems on this page. This will then prepare you for the group activity on Wednesday, all right? So you can read afterwards, you can practice this entire page. So that said, let's pick up with, say, this equation one last time, okay? So just to review that again, let me stop the share. All right, you can see that that looks slightly different from what I said here. So if you're looking at page 42, I actually had an extra term in here and here. So let's see what I'm doing and show you some common pitfalls of doing these calculations. All right, so let's start with the acceleration definition. Let's say that's the derivative of velocity. And again, these are both vectors. We're ignoring the I-hats for right now. All right. What I did next is I cross multiplied. So, and I'm going to switch the sides. So dvx, just because it's easier for me. Again, I cross multiplied. All right. Now I want to get rid of this derivative. So I'm going to integrate. And this is where things differ for a physicist than they might for, say, a mathematician. I recommend doing the following trick. Here, I'm going to go from some special time I'm going to call t initial to some final time I will call t final. Basically, I'm making the limits explicit, right? Instead of doing an arbitrary indefinite integral where you always get plus c, plus c, plus c in your calculus class, we're going to do a definite integral. Now, if I'm going from the initial time to the final time, over here, I should have limits as well. Otherwise, this sentence doesn't make sense. So what would be a good lower limit for a dv integral, if you had to guess? Here we were doing a time integral. We went from t initial to t final.
Initial velocity and final velocity.
Exactly. And if you do this, we don't have to worry about that pesky plus c constant. You could do it that way and it takes some extra thought, but this way works great. And I've discovered this seems to be just, I don't know, this helps me just fly through these problems a little bit faster. Now, let's do this integral on the left. What is this integral? Don't overthink it.
1/2 d squared.
On, oh, well, just this side here. Remember, oh, so if it helps, let me just ask you this. What do you get when you do the integral of dx? Let me help you out even further. Do you agree the integral of dx is the same thing as 1 dx? What do you get when you integrate 1 dx?
So it's just x.
X. So now, what do you get when you integrate dvx?
So just bx.
Now, in this case, is this legal then? Just let me get this written out. I want you to tell me what I did wrong, basically. What did I screw up?
You didn't plug in the VI or VF?
Exactly. And remember, we're doing that so we don't have to think about that pesky plus c. The idea here is velocity is not the integral of a dt. Change in velocity is the integral. Do you see the subtle difference there? Velocity is not the integral of a dt. change in velocity. When I work this out, I get V final minus V initial. That's delta V. And I guess this is X, so I'll put an X there. Now, in a math class, every time you do these problems, the initial velocity is always 0. So if the initial velocity was 0, then sure, velocity is the integral of acceleration dt. That's why in your math classes, they usually start with 0 initial velocity. However, what if you, I don't know, throw a rock downwards and there's air resistance? Well, then the initial velocity after it leaves your hand might be non-zero, and this term could matter. All right. So that said, if we look back, sorry, give me just a second. That is where this extra term came from. Right? If I move this term over to the right, I get that equation that I just showed. I get this thing right here. So that's all I'm showing you there. Now remember, if we are going to do this procedure, this is only valid. Could you please write down in your workbook, only valid if the acceleration is a function of time. Okay? Only valid if acceleration is a function of time. All right. Questions on that? Hopefully you've seen a little bit of this in your calculus class at some point. Let's try this out. Okay. Let's look at this problem now. Let's get to a real problem. That way we learn the idiosyncrasies of a real problem, not all this theory. Okay. In this case, let me scroll down just so we got the whole thing on that page. Can I get that? There we go. Sorry, I got some Zoom windows driving me crazy. All right. Let's look at this. Here we have the velocity. Just remind me, what are the typical units for velocity if we are doing a physics problem?
Meters per second.
So I'm going to say the units of V, whether it's a vector or not, equal meters per second. What are the typical units for time?
Seconds.
Seconds. Now, obviously, you could have milliseconds, but you could convert those to seconds. You could have feet per second for velocity, but you could convert that. So what are the units on this number 2? What do the units have to be?
Meters per second.
Exactly, because we know the output needs to be meters per second. What are the units on the number 8? Somebody else. What are the units for the number 8? Remember,
Meters
there's
per second squared.
exactly. So let's check. If I put in meters per second squared here, then I multiply by a seconds, I get meters per second. And similarly, this one should be what? Meters per seconds cubed. Is that right? I think so.
Yes.
Thank you. So the idea is we're doing physics now. Units matter. This is a step you don't usually do in a math problem. When you're doing a physics problem, it's important that we understand the units implied on each number. So that's part A, what units are implied. Before we go on, any questions on that? Remember, the units of any one term have to match the units of the output. Sorry, go ahead. Oh, all right. Okay. What do you think? Let's go to part B. Can we just use this kinematics equation right here? Delta x equals that crap. What do you think? Why or why not? That's a kinematics equation we have, delta x. Does it apply to this problem? What do you think?
I would say yes.
Why do you think? Well, let me rephrase. The answer is no.
Oh, okay.
How can you tell it's no?
Because it needs calculus.
Well, that's true.
Because it's not constant.
What is not constant?
Accelerate.
How can you tell acceleration is not constant? You are correct. How can you tell acceleration is not constant? How do we get acceleration?
Because if you take the derivative of the velocity, you see that
It's not
What's the-
constant. Yes. Who was that? Whatever. You did a great job. I can't see who you are, but nice job. Okay. So thanks. All right. Take a look at this. If you take a derivative of this term drops out. This term becomes a constant, but this one becomes what? Negative 6t. And that acceleration, if I just take the derivative, I'm getting lazy with my vectors here. If I take the derivative of this thing, I should be able to get, I think it's what, you could tell me if I screw it up here, and I'm lazy with sig figs and crap. I think it's 8 minus 6t if I did it right. And let me check the chat really quick. Okay. Understood. The person that just sent me a chat, I got it. Okay, thanks. All right. Now, okay. So I just want to point out, a lot of students like to grab this equation right here. Sometimes that's not true. If you're not sure, try to figure out the acceleration, and you may have to take more than one derivative, right? What if I gave you position as a function of time? Well, you could take a derivative, then take another derivative and see if the acceleration is constant before you use this equation blindly. Do not trust this equation. It would be approximately correct if you put in the right set of values, but it would not be exactly correct. All right. Again, so Isaac, this thing has to have units of meters per second. That means this entire thing has to have units of meter per second, and this entire thing has to have meters per second. And so we know that time has units of seconds. So here you'd have seconds, second squared. And remember, if you could always follow along with the solutions, if you, right? Because everybody's got different situations. Let me see if I could bring this up. What is this, 2.39? Here's a cool trick. Remember, if you want to get to 2.39, get in this file, hit Control F, and type 2.39 to pop right to it. What? Let's see if we can find it again. There it is. Sorry. I must have hit it twice. So, right, this shows you, I guess, yeah. If you tried these and plug it in, notice it would work out, right? Because if you put in a time here in seconds, that would cancel one of these. If you put in a time here in seconds, that would cancel two of those. So that's how we know. All right. All right. So remember, you've got the solutions here, but you may want to follow along with the solutions. You may want to follow along with me. You may want to have both, whatever you want. Okay. So, all right. All right. So let's look at this one. Part C. Speed and velocity are similar, but not exactly the same. What is the initial velocity in this case? Well, if I want to know the initial velocity, that's just saying t equals 0. That's the initial time, t equals 0. So if I plug in t equals 0 into there, what is the initial velocity?
-2.
-2. And then just because I'm being thorough here, I might as well, I could put in the units now because we know what the units should be. So the velocity is -2 meters per second I hat. What is the initial speed?
Just -2.
No, it's not -2.
Oh, sorry, just 2.
It's 2, right? It's the absolute value. So, right, another way to say this is sometimes you might see this like this. The velocity is equal to, I'm getting lazy with sig figs again. It's 2 meters per second in the negative I hat direction. This first part is the speed. This means to the left. To the left. I better write that out just in case. All right. So the idea there, that's the difference between speed and velocity. This is something you need to watch out for all the time in these problems. If a question asks you about speed, that is not the same thing as asking for velocity. If it asks for speed, you got to remember to take an absolute value. All right. So let's see if you could try the next part. Figure out the magnitude of the initial acceleration. Let's go ahead and do that. All right. And I'm going to write this thing up here on my board. This is 2.39. Our velocity equation as a function of time.
Is it 8?
Probably, I don't know.
8 meters per second square.
I'm going to catch up. Hold on. I'm just getting this on my paper. Okay. So we already did parts A through C. Part D says mag of initial accel. Well, from there, I know that A is equal to dv dt, and I'm going to be sloppy with the arrows. You're supposed to know the arrows, the I-hats, the units are all there, but in order to get through these quickly and fit them on a board, we have to do this. So we said, what was this? Take the derivative. I think that was 8 minus 6t. And so, when you plug in t equals 0, you're right. And so in this case, we don't need to worry about any absolute value because it happened to be positive. So in this case, the magnitude of the acceleration is 8. The acceleration would be 8 I hat. And yes, we forgot the units. So again, to be clear here, I'm going to be pretty lazy with units and I hats. On your final answers, as Esteban's pointing out, we would probably rewrite this as 8.00 meters per second squared in the I hat. To save room on the whiteboard and to save us time, I will probably not write this all every time for this problem. So remember, you've got the solutions where I had a little bit more room to write. But absolutely, that's all in there. Okay, so just be aware I'm doing that for this whole problem. Let's get back to it and see what's next. So we did part D. Ooh, jerk. Not just a term to be used for your physics instructor. It's also the time derivative of acceleration. Let's take a look at the jerk. So in this case, we are told this new piece of information. So in E, they say jerk is defined as the derivative of the acceleration. Think about this. If your car, if you step on the gas, you're changing your acceleration. You feel the car jerk forwards. So that's kind of how I think about it. If you have a change in acceleration, the car jerks forward. All right. Or if you slam on the brakes, you change the acceleration and you feel a jerk like that. Okay. So here, this is pretty easy. We're going to get rid of the vector symbols because we're lazy. We're going to forget about the units, forget about the sig figs because we're running out of space. And so here, this would be just 8. Aha. That's cool.
Wait, isn't that -6?
Oh, whoops. Sorry, -6. Thank you. I looked at the wrong number. My bad. Yeah, 8. The derivative of 8 would be 0. This one would survive because it's got the t. Sorry about that. So the jerk is -6. The magnitude of jerk, sometimes we write this with these absolute value, would be 6. What should be the units? Think about this. Look at this equation to figure out the units right here. Somebody other than Esteban. What should be the units of jerk?
meters per second cubed.
Nice job. Okay. And this is, in fact, probably what we found up here for the units of that number 3, I hope. All right. So there we go. So far, so good. All right.
The board's a little cut out in the picture.
Whoops. There we go. Let me, yeah, thanks for, is that better?
Yeah, it's a lot better. Thank you.
Yeah, sorry about that. And again, since this problem's solved there, you could also, if I'm ever really bad, you could check the solutions as well. But I'll try, and thanks for giving me the heads up for sure. All right, let's go back and see the next part. So now we've kind of done parts, we've done all the easy stuff. We've done parts A through E. Actually, we did part of F already, didn't we? So I'm just going to read here. I think I'm going to say we completed A through E. We did those. Part F says get the equations for x of t and a of t. Well, we already figured out the acceleration as a function of time is equal to, I think we said it was 8 minus 6t, and we're ignoring I hats and units and sig figs. And now we want to get x of t. All right. So how would we get the position as a function of time? What should I do?
Take the integral of that velocity.
Okay, so we take the integral. You said take the integral of that. So again, sorry, this glare is driving me nuts. I'm going to try and fix it. There we go. All right. So what is the equation I might want to write down? Let's just go back to our workbook and look at it. Right up here. We know that's, oh, whoops, we want to get x. So we know v of t. We know it's a function of time, so we could do this. So I'm going to write down that equation. And if you want, you could race ahead. Remember the answer. All right. And now I stuck in limits here. Instead of going from t initial to t final, I just said, let's call t initial 0 because that's what almost every problem I've ever seen does. Not always true, but in general, we want to go from 0 to t final. Okay. Now, when I do this, let's go ahead and plug in the steps. Let's see, what was this? We're going 0 to t final. Velocity was -2 plus 8t minus 3t squared dt. All right. And what is x initial for this problem?
It's unknown.
Nope.
Or it, okay.
-2.
What is it? It's not -2.
0.
No.
2 meters.
Read the problem.
2.
Oh, wait, it is -2. Whoever said -2, you got the left. I didn't see the left at first. So now I thought you were saying -2 because of this -2. It's -2 because of this -2. So whoever said -2, you were correct, and I apologize. I didn't see the to the left when I first read it. It's initially 2 meters to the left. That's what says x initial equals -2. And let me check the chat here. Always read the problems. Yep. Okay. It's hidden in there. So basically, now you know what I might do on a test question or something like this eventually, right? If I give you this kind of problem, I almost always do this, and I almost always make the initial position negative just to see who reads to the left. And you see, I caught myself too. So don't feel too beat up if you screw that up once in a while. That said, if you practice these problems, you'll get used to my tricks. I wrote this book. You'll know it. All right. So here, this one, we did all that work to figure out this number, -2. This is one of the practical issues with doing this. This is what's different from a calculus class. In a calculus class, this is almost always 0. Well, from here, let's see. What are we going to get? -2t plus, what is this? Is that 4t squared? Remember, it's going to be t squared, so I have to divide by 2, and then, I'm going to get a t cubed over 3, which gives me -1 t cubed, I think. And this is actually the equation of motion for constant jerk. Notice this is 1/6 of the jerk. We found the jerk was -6, remember? And then here, the initial acceleration was 8. So this is actually 1/2 of not A, of A0, the initial acceleration. This is the initial velocity, and this is the initial position. Sorry, let me lower it. The idea here is, what if we had an equation where you had constant jerk instead of constant acceleration? This would be the way to write the new equation of motion. And I guess to be consistent, I should call this A initial, but whatever. It looks very similar. Like if we just had this part, it would be constant. Sorry, if we just had this part, everything over here, that's a constant acceleration problem. Now we have an extra term. You could memorize this, but why? The idea is memorize the procedure. And that works for every problem, whether it's a polynomial, sine, cosine, you name it. All right. I'm going to pause and see if there's any questions about that. This was a tricky part, and then this was just for fun, for spice.
So in what situation is jerk not constant?
Almost an infinite number of situations. So, for example, if you have an oscillation, let me give you an example here. Or what if you're driving a car, right? At some point, usually when you're driving a car, let's say you get on the freeway, at some point you're going to be driving in a straight line at about 60 miles an hour. At that time, your jerk is 0. Your acceleration is 0. So there's a case where just in almost everyday life, jerk will change just like acceleration changes all the time. When you take your foot harder off the gas, or if you pedal harder on your bicycle or whatever, there's going to be times where you jerk and times where you don't. Is that good on that?
Well, what I was thinking was when acceleration is not constant, then your next derivative should be a constant jerk. So I was thinking,
let me give you an example. That's your first approximation, Esteban, but it's rarely accurate. Okay, let me give you an example of this. What if this is your position as a function of time? Okay, can you see that all right? 240.
Mm-hmm.
If you take a derivative of that, what's the velocity? How do you get the velocity?
It would be sine negative a sine.
Let's see. Derivative of sine is cosine, which means derivative of cosine is negative sine.
Okay, so
and then omega pops
sine
out. So this would be A omega sine omega t. Okay. Mm-hmm. Now the idea here is I use the chain rule, right? First you take the derivative of the function, then you take the derivative of what's inside. Omega is this constant. It's basically like your RPMs. Okay, so omega is a unit that has units of radians per second, which is equivalent to RPMs. So notice, check the units. This is meters per second. A is a thing called amplitude. That's how far the piston is moving. So that's meters times omega has units of radians per second. Radians is a placeholder unit. Notice the first thing I'm doing is understanding the units, everybody. Meters times radians, that's equal to just meters per second. So we see this has units of meters per second. This crap is a function. Functions have no units. So we see that the units match. Now, I'm doing this to answer your question, Esteban. Just think, if you keep taking derivatives, do you agree it's
Yeah.
just going to keep flipping back between sine and cosine and sine and cosine?
That's exactly what I was thinking when you were showing me that. So,
And do you
but-
agree jerk would not be constant?
yeah. So the only time jerk ends up being constant is when it's like a polynomial, right? Because eventually the derivative has to end with a
If it's
constant.
a third order polynomial or less. Yeah. If it's a fourth order polynomial, jerk can change. So basically, what if I had extra terms here? What if I had a t cubed or a t to the 17th, right?
Yeah.
So if I have a large power of time, jerk isn't constant either.
Okay.
There's a joke if you look on Wikipedia or something, right? They say the time derivative of jerk is snap, then the next one's crackle, then the next one's pop. I don't know. That's old school Rice Krispie humor. Right? It's not that good, but you could check it out on Wikipedia and not laugh as well. All right. Yeah, but so, okay. That was a good question. Getting back to this one, I think we addressed that, right, Esteban?
Yes.
Okay, cool. So what did we do here? We took care of this part. Ooh. All right. Now we get to the physics. All that was math. We have to, so notice this. In these types of problems, you have to be proficient in math before you can do any physics. Yay! One more boundary to your learning and success. But it's fun. So hopefully you can fight through that. So what does this question mean? Is the object moving to the right? What time intervals? What am I really asking there? Do you know? Could you rephrase that in terms of these symbols, maybe?
So when velocity is positive?
Yeah, this is another fancy way of saying when is v greater than 0. Someone give me one way to do that.
Put it in an Excel sheet and plug in numbers.
Beautiful. That is a classic thing you could do. Now, just to show you, you might be thinking, oh man, I don't want to do all that. It's not that bad. We're going to do that in class, in lab this week. So if you're bad at this, this is how you could do that. You could come into here. You could put in some numbers up here. What was it? I think it was -2, 2, 8, -6, or whatever these numbers were. And then you could make a column of time, right? And you could pick an increment size and you could plot it. You could do this. And then you could put in a formula equals, etc., blah, 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 and do all the constants and stuff. Again, we will show you how to do that technique in lab. Now, some of you might know you could also just drop the function into an online plotting program or stick it in your graphic calculator. All good ways. Great. What's another way we could do this to get the exact values? Because plotting will only get us approximate values, right? It depends on how good your plot is. What's another way you could do? Oh, whoops. Sorry, wrong share. What's another way we could figure out this?
Could you set the velocity equal to 0 and find it when it's positive?
Exactly. And that's really useful on test day because eventually it's faster. Set v equal to 0, solve for what?
Solve for t.
Yes. Awesome. And so if you do that, that tells you the special times where velocity is equal to 0. Then in combination with your plot, you could get an exact value for the crossing. All right. So to save some time, let's look at that one in the solutions here. That was part something or other. All right. We did that one already. Okay, so it's moving to the right with this. So basically, I had to do the quadratic formula on this. So I found these times, right? And so then, like I said, make a plot and you could see that, and we'll discuss that more. Now, here's the other thing you could do. We know at time equals 0, the velocity is negative in this special problem. We did that in part right here, I think. In part C, we said the initial velocity was -2. Sorry, I'm scrolling. So we know that, oh, come on, marker. Where are you? We know at t, oh my gosh, come on. T equals 0, velocity was less than 0. That means at this time, it crosses the axis, so then it goes to positive. And then again, after crossing again, those velocities would be negative. So in this case, you could use the initial velocity and the crossings to figure out time intervals. And that's actually really fast. A lot of you probably have a quadratic formula thing in your calculator already. Again, this is not the be-all, end-all. Almost certainly, to make sure you didn't screw it up, you would plot it as well and see if these numbers look about right on your plot. Good job. Let's go back to here. I'm going to pause for a second. Are there any questions on that? What do you think? Doing okay? A little bit? All right. Let's go back into it. Okay, so where were we here? Okay, how about this one? What do you think we need to do here? Or what should we watch out for in part H?
Do we just solve slowly, like go from time and then solve position? And
Yeah, you
solve
take
that.
this time and do what with it?
Then you solve position.
Yeah,
and
you
then
stick it
go-
into that x of t equation. Good. I'm
Yeah.
just writing down what you're saying. Okay. And then what?
You just got to keep working your way up, right? So then position to speed and then speed to
Okay.
acceleration.
So when you take t and you stick it into, you take this, right? You'd shove in t equals 3 in there, get the number, and then same thing for acceleration. What were you going to say, whoever unmuted?
I was going to say that would not give you speed. That would give you velocity.
Exactly. We have to watch out. So I snuck one in on you. Look out here. Speed is the absolute value. So this one, I was trying to be sneaky. Here, you'd have to take the absolute value. Sorry for red-green colorblind, Jesse, if you're in here. Absolute value. About 10% of, I think it's 10% of males are red-green colorblind, and 3% of women, something like that. But yeah, so position, this is a plus minus number. Sorry, you can't read that at all. Basically, let me click somewhere else so I can annotate. Position, that could be a positive or a negative. Speed has to be only positive. Take the absolute value. Acceleration could be positive or negative. If I said magnitude of acceleration, it would only be positive. So just watch out for that. All right.
That was sneaky.
Oh, I'm sneaky. So you see the time. And so if you do these problems, you'll know my kinds of tricks. And don't forget, there's going to be practice tests you could do later. So then you'll actually get a genuine test of your abilities and see if you catch my tricks in a test. We'll worry about that later. Okay. So how about this? If I want to figure out how far the object has traveled, how do I do that?
So the absolute value of on the x position.
Okay, start sooner or start earlier, right? So I guess let me rephrase. We know x initial, right? And do you agree we're going to know x at time 3 seconds?
Right.
So what were you saying to do with these?
Well, you need to know the inflection point, so you know which so you want to get the absolute value.
Okay, so I'm still listening here.
I don't know how else to explain that.
Okay, let me start by saying this. I want to address Nick Quang's point in the chat. Nick, that is the trap I was looking for you to use, and that is wrong, Nick. It turns out, remember, it turns around at these two weirdo points in time. I think it was at t equals, let's say it was about 0.27 seconds, I think. And I think it was also at, well, I've got it right here. Oh, somebody's got it. Yeah, let's go over to here. This is what you got to watch out for. And let's go to the solutions. Look, we know it turns around at these two times. All right. So if I do all this, notice we get the position at 3 seconds is right here. Let's just go look at the solutions. Ugh. Ugh. How about I write it like this and see if this makes sense? Here's the position at time equals 0. Oh, that should not be italicized. I'm a bad person. Here's the position at this time. Here's the position at this time. And here's the position there. So notice I did this little chart right here and see if that makes sense to you. Yep. And so this is the thing I wanted you to watch out for. If an object reverses directions, if an object reverses direction while it's traveling, you can't just do what Nick suggested. If the object does not reverse direction, you can do what Nick suggested. So basically, I don't know a shorter way to explain it than this. So I'm going to pause for a second and let you get a feeling for it. And maybe I'm going to scroll down just a little to see if we could see this. Let me do 180 here so I get the whole thing. All right. So when you look at this one, the idea here is this. From 0 to this time, that's about right here. It's not perfect. 0. I think it was 2.8. It's closer to 2.8, right? There's a displacement right here. That distance is negative 2.68. So right here, the distance between it starting and right there is negative 0.27. Whoa, that's crazy that they happen to match up that closely. It's just a coincidence that this time interval is 0.28 and this one is 0.27. It's just a coincidence. Notice its displacement is negative 0.27. It goes down 0.27, but the distance traveled is positive 0.27 to the left. Now, from this point right here to this point, right about there, what time is that? This is about this is about 2.4 seconds, I think. During that time, the displacement from here to here, it goes up about 4.7 meters, 4.7 meters up. Now, by up on the graph means to the right in real life. I'm going to say that again. Here, the value of x goes up. That's the same thing as going from a negative value to a positive value. That's the same thing as going from the left of the origin to the right. So here, when I'm plotting position versus time, going upwards on the graph corresponds to the object moving to the right. And then finally, we see here, it goes down or to the left, however you want to think about it, about 1.4 meters. Okay. And so, and let me, just to be clear, this was the time in seconds, and this was the meters it got displaced. I'm going to see if you guys have questions about this. Is this making any sense whatsoever?
So, Professor,
Yeah.
do you basically just integrate separately depending on like if it was like going one direction or the other? Like as soon as it changes directions, that's like going to be like,
you could do that. Here's another thing you could do too. If you guys want it, right, we have Google. So let's just show you here. Let me see, what was this one? Hopefully it's your final exam and then, oh, whoops, where am I? All right, let me just open up a new browser here. So hold on. Oh my gosh, come on. Let me, sorry, getting used to the two screens here. Now you could see this. And then, oh my gosh, Zoom. Come on. Zoom. Sorry. So if you go to here, right, one thing you could do, and I think that was Dom that was talking to me, right? If I just type integrate, you could punch in the equation, whatever it was, and we could do, oh geez, I've already forgot the equation. I've got it written behind me. It was -2 plus 8t minus, what was it, 3 star t squared I forget what the exact time was. And I think it's this. I may have mistyped. Gosh, get out of here. And so notice it could give you that area for you, right? So it's doing that other thing. And you could plot this thing, and then we could change this from 0.28 to, 28 to, what was it? I think it was 2.4-ish. That's the next region. And so you could get these values this way, or you could even stick on an absolute value here. Let's see if this does it. Let's see if it does the absolute value for us. And so notice it could even do that for you there. So Dom, that's how you could do that. You could integrate those piecewise if you wanted to, if you want.
Okay.
Does that address your question?
Yeah. Okay. Yeah, it does.
And I mean, let's face it, in the real world as engineers, you do not want to be doing this stuff by hand. So, you know, as a student, when you have a face-to-face class, which you probably will have some in your career, fingers crossed, you have to learn the calculus too. So I would not get lazy and totally rely on that, but why not use it to check your answers, especially in a test environment online? Use that to check your work. Or if you're running out of time, hell, just use it on your test. I don't care. But I do want you to try and practice doing integrals by hand and then check it and see if you screwed up. And it'll show you step by step so you can see where you made your mistakes. So try to use this time to check that. Other questions?
Wait, what was that search engine that you, was that a search engine that you were using?
Wolfram Alpha. And so if you want, I put a link to it in the welcome module in Canvas. Again, I put a link to that in the welcome module in Canvas. And I told you some stuff to try. And there are times there will be problems that you can only solve using that, at least in a practical time scale, such as solving a cubic equation. If you try to solve a cubic equation by hand, you will screw up, almost certainly. Hey, there you go. All right. Let's get back into it and see if I forgot anything in that question. Whoops. Okay, and here, like I said, we are going to practice this on Thursday in lab. I'm going to ask you something here. Just ask yourself, you don't have to answer, but I want you to think to yourself, did you understand the problem more when you saw the graph and thought about it? I did. I hope you did. And that is why we need to learn the graphing techniques as well. All right. So that said, this is a good spot to take a break. Let's take a short break. Everybody can use the restroom, come back. I'm going to leave the live stream running. Sorry. But yeah, go ahead and take a quick break. I'm going to get some more water, and I'll see you back here in like 7-8 minutes, and then we'll start up again. Okay. So take a quick break. So we're still on break, but if anybody has any questions, I'm ready to answer any questions you have here.
How was your camping trip before Thanksgiving?
Oh, it was pretty cool. Not long enough. So, but I did decide to take a camping trip over winter break too, and that was pretty good. So I got a little bit more time in there. Yeah. Did you do anything interesting or no?
Just pretty much stayed here. I mean, the whole concept of Thanksgiving and Christmas kind of ruined this year.
Yeah.
Or this last year.
Yeah, right. Well, yeah, I mean, I guess for me, because that's somehow I've got this agreement where I don't have to do anything related to family over Thanksgiving. So that was pretty nice. And I don't know. I don't really like hanging out with my family. I mean, they're nice and all, but I just don't want to see them. So I was kind of glad about that. I know that I'm kind of unusual in that respect, but
So were you camping alone or you were,
yeah, I go out, I can just walk around in the woods and I don't know, make instant mashed potatoes and look at trees.
that's interesting. You were out there for 3 days? A couple days?
Yeah, I think it was 3. So it's good though. Yeah, and I mean, when non-COVID times, I can go with a group of guys too or something. So we call it man weekend. So I get to escape the children and yeah, I don't know. It's just kind of our, I don't know, fun time. So being away from screaming children for 3 days is always good.
Professor Joystein,
Yeah.
on problem 2.39, you know how we did the integration and our points of integration were like from time 0 to time final?
Okay.
Do we
After
plug
the
in
fact, I
integration?
changed T final to the letter T.
Okay. But
The
do we
reason,
plug it
oh,
in?
sorry, go ahead, Luke.
Do we plug in the points of integration?
So you can plug in specific values, but the idea there is, hold on. Just, I think this will help if I show it here, right?
Okay.
So you're doing something where you get V final equals V initial plus the integral of, let's say we were, what was it, A dt, something like that, right?
Yeah.
So now the idea here is I don't like writing the letter T up there because it's a circular reference between the integrand and the limits. So what I do is I say T final, and then as soon as I do the integral and plug in the limits, then I change T final to the letter T. That way it's not confusing to a strict mathematical definition of the integral. Does that make sense why I'm doing that? You could write this and this would probably make more sense to you as a student. It's just not rigorously mathematical correct. You go from 0 to some arbitrary final time, and that gives you an arbitrary final velocity, which is the equation v as a function of time. The idea here is the final velocity will depend on the limit you choose, right? It'll depend on the value of t final.
Okay.
And so that's why we say v final is essentially velocity as a function of time. Whichever t final you put in, I'll get a different v final. If you put in a different limit, you get a different answer. That's why this is, I change. So after you do the integral, you'll get, say, v final equals some number plus some, let's say, crap times t plus some crap times t squared plus some crap times t cubed maybe, or something like that. I don't know. Right. But when you do that, isn't this essentially saying this is the velocity as a function of time? You tell me the time that you want to stick in your limit, I will give you the velocity.
Okay.
Is that helping?
Yeah.
Yeah, that's a subtle point, and I glossed over it and I forgot to talk about it. Good question. Others? Right on. Okay, well, this is probably a good time to get back to it. Now, it's been about 10 minutes, so let's go back and I want to share a screen share. Now, okay, we've been talking about non-constant acceleration, right? And at some point, we see that there was this technique where integration. I do want to point out one extra thing. This is kind of, this is some terminology here, okay? So a differential equation is an equation where you have D's in it, all right? Now, the solution to a differential equation is the answer for what V is. So notice this, come on. This has a differential of V and a differential of time, right? The solution does not have differentials in it. So this is differential velocity, this is differential in time. Now, what's going to happen if A is not a function of time? What if A depends on the velocity somehow? For example, air resistance or something like this. All right, so let me scroll down. Oh, whoops, I got to clear those first. Here is a more challenging differential equation. So let's say for some reason the acceleration is supposed to obey this ugly equation up here, this nasty thing. The trick is first rewrite the A. A is always defined by the time rate of change in velocity. Now, this is an important step. I call this step 3 down below. So I'm going to put a bullet on this, right? So here's step 1, write the equation. Step 2, rewrite it using differentials. Step 3, separate the variables. I get the V's all on one side of the equation and the T's all on the other side. Then you can integrate and everything is exactly the same as what we just did. And so this is the solution to that differential equation. Now, separating the variables is one technique that works for some differential equations. This does not work for all differential equations, but I just wanted to show you how you would handle this, okay, if you were curious. And this is on page 49 in the workbook, if you're curious. Sorry, I forgot to say that at the start, 49. Okay, so here are some things. Most problems typically start at t equals 0, and v initial is not necessarily 0. So this term here that came from the definite integrals will not necessarily pop out. But this saves us the time of figuring out that constant c. Remember that the integral of dv is not v, it's delta v, right? It's a change in velocity. Okay. And this is basically the same thing as you either say it's delta V or V plus a constant, okay? Now you might be saying, well, isn't the constant always V initial? It turns out no. Okay, this goes to the question I was just answering for, I think, Luke that was. Strictly speaking, you shouldn't have T in the numerator end up in here, right? So we can't have, we can't have T in the integrand end up in here. So you might notice first I do the integral and plug in the limits, and then notice what I do afterwards. All the T finals, I just change to the variable T. And then in the last step, once I solve for V final, I just rewrite that as V as a function of T. Why? If you plug in a value for time and the known initial velocity, you are going to get the final velocity at that value of time. So that's this last step of this process. All right. And I want to point out when A depends on V, step 3 cannot be skipped. So that's right here. If your acceleration has a velocity in it, we have to separate them before we do it. Let me give you another example. Here's the most common mistake people make. So here is a very common physics model. Drag at high speeds is proportional to velocity squared. So it doesn't just increase with velocity, it increases according to velocity squared. So the faster you go, you really get a lot more drag. So this is what students often do. They'll write this down, then they'll say, oh, well, that's just this, fine. And then they'll try and just integrate it like this. This doesn't make sense because this V was not separated. Okay, so it just doesn't make sense. Or don't be a bad monkey. To fix the mistake, all you have to do is one extra step, right? Compare this step right here. Sorry. Here, I did the integral without separating. This is not true. Okay, so this is not true. Here, I separated it before I integrated it, so this is okay. And then this is a constant. You can do this integral. This depends on v. You can do that integral. If you're curious about this stuff, these are some of the common differential equations that appear in a physics class or the first 3 physics classes. So believe it or not, all of these differential equations show up in your first few physics classes. Not all of them can be solved with this separation of variables technique, but a lot of them can. Well, yeah, let's leave it at that. Okay, now before you freak out, let me be straight with you. I think it's useful to look at this stuff. I think if you're a physicist, it's useful. I think if you are going to take physics 163 with me, some of these problems are useful. However, I'll make you this deal. On a test question in my class for physics 161, usually the straight up just integrate will work. I might give you an extra credit question where I ask you to do separation of variables. So to be clear, I think you should learn this. I think it's a good skill, but if you have to pick something from chapter 2 to throw out, it is the separation of variables questions. Understood? It is useful. We will use it again in our class. It might be an extra credit question on your test, but it will not be a regular credit question on your test. Enough said. Any questions on separation of variables and the fact that you do not need it for this class? It's just recommended. Okay, good. Making that clear. All right. So now that's all the stuff that maybe we didn't cover in Physics 110. Maybe we should try some other problems now. Let's go back to here. So again, that's all right. So let's go way back. Where's my, oh, there it is. All right. What the heck? Let's maybe work backwards. Since we've already been talking about graphs, I want to try and talk about graphical understanding. Okay. So if you can, oh, sorry, this is taking me so long. Let's go to page 31 in the workbook. 31. Okay. I'll give you a second to get there. All right. And so we're going to do this chapter in a little bit weird order. We first did the calculus. Now we're going to talk about the graphs, which helps us understand that calculus. And then we'll go to word problems. Okay. All right. The big deal here is this. Let me get this off of here for a second. If you are going to do any kind of science or engineering, computer science, whatever you want to call it, almost certainly graphs are going to be involved. These particular graphs are not the be-all, end-all of anything. What we really want to get out of this section is you learning some basic techniques as reading the axes and understanding the units on the axes so you can understand the units of the slope and interpreting what slopes mean versus areas and what these things might mean and how to check the units to figure out what they might mean. That's kind of the big picture, what we want to do. Looking at a graph, creating a graph, that's crucial for any science or engineering application. And then understanding it and interpreting it and being able to help others is a huge deal. Almost any real talk and any real job, right? You're going to have to explain a graph. And so that's really what we want to get used to. To that end, this is easy stuff to graph, so we're going to do it. That doesn't mean it's easy to understand. It's easy to make the plots, but also understanding them is tricky. Again, I will focus on making these plots on Thursday in lab. But that's why we are doing this. It's graphical literacy. Essentially, you need to understand graphs in general. So we're going to take some particular graphs and learn about them. Great. So here we go. We're going to have some plots of motion, and we're going to analyze these things. Now, if you have this open, I'm going to bring up a simulation in just a second. I want to point out a couple of things here. On the XT graph, the horizontal axis is time, the vertical axis is position. We just looked at one of those. We're going to do it again. Remember, X is position, not distance. Okay, and then there's a bunch of things here about that. You could read that while I'm getting the simulation ready. And then notice there's the velocity graph. And I want to point out the velocity graph I like to spend a little bit of time on. Now, let me mention a couple of quick things. You know the slope at any point on an XT graph is velocity. That's the derivative. Remember, slopes, derivatives, same thing. Similarly, the slope of a VT curve is acceleration. Now, be careful. The area under a VT curve is not position. It's displacement or change in position. It's delta X, right? When you stick in those limits from initial to final, you do not get X. X would be position. You get delta X, X final minus X initial. That's kind of our warm up. So if you have this page out, I want you to read that while I get the simulation running. So again, this is page 31. I want you to keep that out in front of you while I bring up a simulation. Okay. So let me see if I can bring this up. Whoops. Let me bring up another one here. Where is it? Okay. Zoom, get this thing out of here. Come on, Zoom. I will do. So if you want to play with this on your own, the FET is called the Moving Man FET. So I just Googled Moving Man FET. I'll throw that in the chat. So that's what I Googled to get this simulation. But for now, you can just let me play with it. And then let's get the Java version. It runs a little bit faster for me if I do the Java version. Sorry, I forgot to do this on the break. Is it going? Did I not click it? Oh, wait. Zoom was hiding it. Sorry. Zoom. My favorite thing ever. All right, so there we go. All right, is that running? There it goes. All right. So what I'm going to do, this is a simulation that only gives constant acceleration examples, but let's do one here. Let's say we had -4. Let's say the velocity is initially 4 and the position is initially 0. Let's say it's -2, just to mix it up. All right, so the idea here, if I run this thing and play it, I don't know if you could hear that, hopefully not, but I'm going to play it back now, and I'm going to play it back on slow speed. And let's just analyze this motion. So notice the person on the screen right here, initially the position is about -2. Whoops, wrong colors. Let me do that position here in blue. Position initially is -2. The person is initially moving to the right with speed about 4 meters per second. So it's moving right. The acceleration is the other way with size 4. And that's going to have units of meters per second squared. So think about this. Initially, the person is moving right and slowing down. Agreed? Let's watch it. It's slowing down. Look at the velocity. To be clear, I'm looking right here, looking at the velocity right there. It's a smaller number now. Let's keep going. It slows down. And then for a split second there, did you see that? It stopped. Let's run this again and see if I can get it. Right there. For a split second, it stops. Okay. Now notice the acceleration, the bottom value, is not 0. What does this mean? The velocity is instantaneously equal to 0. So at this point, right now, velocity equals 0, but the acceleration is equal to -4. What does that mean? It means the velocity will change and become more negative. Acceleration describes the rate of change in velocity. It's how it will change, right? So if the velocity is 0 and it's going to change, in the next instant, the velocity should be negative. Let's keep going. Now it becomes negative. And now I want to point something out here. If I look at these numbers here, notice velocity is less than 0 and the acceleration is less than 0. In this case, because they're both negative, Deuterino here is speeding up. He's moving left and speeding up. Moving corresponds to velocity. Left corresponds to the negative sign right there. Sorry, I just overdrew it. And then speeding up corresponds to the fact that these are both negative. So you're speeding up whenever they're both negative. You're speeding up whenever they're both positive. You're slowing down when one is positive and one is negative. Okay. Now, if we really want to understand this, sorry, Zoom. Let's go over here. Sorry, Zoom's hiding stuff. I got to move things around a little bit. These are going to be the plots. So notice here, if I could, this is X. The next one down here, this is velocity. And this one down here is acceleration. Okay. And so I think if I remember right, we're going to need to zoom in here a lot. There we go. And then let's go ahead and look at this one now. Let me see if I could zoom this one in. There we go. All right. So all I was doing was adjusting the numbers here. And I think, there we go. Now I've changed the increment sizes. So notice the time scale is down here at the bottom. Time is on the horizontal axis, and these all have 10 seconds right here at the end. So these all have the same time increments all the way across. Okay. And the idea is, if you can plot these things, we should be able to understand everything by looking at the plots, and then we don't need the animation. So I'm going to put in the same information. -2. I think we said this was initially 4. And this one was initially, well, it was -4, I think. So when I run this thing, let's take a look. Same problem, but look at the graphs. All right. And so in this case, if I play this back, I could play this back super slow and we can analyze this. So right now you could see where we're at in the graph. So to be clear, I'm looking at this time right here. This dark bar here is the time that we are looking at in this simulation. Now, let me just get rid of that so that you can see better. I'm going to keep running this one. Notice right about here, that's the instant where it stops. Look at this interesting information we see. Notice velocity is 0. The slope of the xt is 0. Slope of xt is the velocity. At any point, notice this slope corresponds to this value right there. The slope of the xt corresponds to this. Now, wait a minute. What about, whoops, give me a second. This area right here. What does that area relate to?
Displacement.
The displacement. So that area relates to this change in x. That area gives us this displacement. Sorry, it's not perfect there. So notice when the position is going up, When position is increasing, the person is moving to the right. Okay. Delta X is positive, means the person moved to the right on the screen. So, right, the person, the person started out right here and moved to the right. Delta X is how much this person moved to the right. Okay, notice right here, we're going to get a negative area. Sorry, give me a second. Here you get negative areas. That's moving to the left. Okay. And finally, one last piece of information here. This slope corresponds to that acceleration, right? That's the change in velocity over the change in time. Think about it. Rise over run. If you look at the units of rise over run, that will help you remember this stuff. The units of rise over the units of run for the VT plot give you acceleration, right? This has meters per second. So if I have meters per second divided by seconds, right? Meters per second, that's equal to meters per second squared. So that's what I want you to kind of think about here. All right. One last thing. What's this area? What does that relate to?
Change of velocity.
That's delta V. So this area relates to that delta V. So let me just draw it over here. It starts out right here and it goes down to there. That was delta V. And I'm running out of room here. That's supposed to be right there. I don't know how to squeeze this in. All right. All right. So let's, I want to pause, and I'm not going to bring up Zoom. So unmute if you need to ask me a question, or let me see if I could find the chat.
So then in this case, if the acceleration changes, would the slope relate to a jerk?
Yes, you're absolutely right. So if the acceleration changes, do you see anywhere where the acceleration changes?
At the end, it should change, shouldn't it?
Exactly. Because remember what happens here. Let me play this. Okay. Accelerations to the left, accelerations to left. I don't know if you could see that guy moving at all. So there might be some lag. What's going to happen when this guy hits the wall in a half second? I paused it. When the guy hits the wall, boom, he stops, right? That means the acceleration had to change. So there was a question here about this point in time. Do you agree that the acceleration changed there? And so we see that the acceleration changed, and we could get the jerk is equal to the change in acceleration over the change in time. So that would be going a step further. To be clear, this is approximately equal to delta A over delta T. And if you wanted to figure out the jerk, well, I noticed up here the clock is running in approximately 0.1 second time intervals. And then you can see that the acceleration changes from, we do A final minus A initial. Well, A initial was -4, and A final looks like something like positive 20 or something, maybe. I don't know, 25. So you could actually get the jerk from that. I don't know who asked that, but did I address your question?
Yeah, that was perfect. Thank you.
Cool. Other questions? Sorry, this is so messy. I wanted to erase all my drawings and just play this one more time, okay? But does anybody else have any questions before I erase my drawings? All right, and you could always watch the live stream on Rewind and get them back. Okay. All right. So now just so we're all kind of looking at this together, this is what I'm going to do. I'm going to play it back. And the first time I want you to look at, as this is going, look at the relationships between these two plots. Then I'm going to play it back one more time and look at the relationship between these two plots. Okay. I should make one last note. Notice this is A is less than 0. That corresponds to concave down, if you're curious. Second derivative is the concavity test, right? Do you have a max or a min? Well, in this case, you're going to have a maximum because the acceleration, the second derivative, is downwards. So it all kind of relates. So again, let's run this back, compare the top two graphs. Position is negative. Okay, velocity is about to go to 0. We have that 0 slope on the xt. Now it's going left. Now we get a negative slope on the xt graph because the velocity is negative. All right, and then when he smashes into the wall, this is kind of a fun thing to notice. All right, let's call that good on that one. Let's run it back one more time and look at the bottom two graphs. So now this time I want you to look at these two graphs down here. Okay, and so, oops. Let's play that back. Acceleration is negative. You have a negative slope on the VT plot. At the instant velocity goes to 0, the person goes to rest, but acceleration is not changing, right? It's still a negative acceleration. So now we're going to go negative, right? And so when we see this one, as you go negative, very good. And then almost to the last step here, I'm going to start stepping it forwards now. So we have a large velocity that's negative and a negative acceleration. You're speeding up. And then right here at this point, if I could actually zoom out, you might be able to see this better. Oh, I can't see the acceleration. It's off the charts. So that's all right. Okay, but so at this point, if we keep going, notice this. One more step. Come on. There we go. Now we're into this region right here where you have a negative velocity, but you have a large positive acceleration, right? This is a positive slope. Negative value. Is it speeding up or slowing down?
Slowing down.
Slowing down. And notice, what's the speed right here at the end? What's the speed after he smashes into the wall?
0.
0. What's the speed right here? About, if you could eyeball it.
-8.
-8, let's say somewhere. Let's say, okay, how about I just say -8.5-ish? Something like that. So we know your speed goes from 8.5, the absolute value of that, to 0. So it is slowing down. The velocity is -8.5. The speed is 8.5. So essentially, if you're looking at a velocity graph, the closer you get to the horizontal axis, the slower you are moving. Again, the closer you get to the horizontal axis of a VT plot, the closer you get to 0 speed. All right. Now, if you're curious and want to do this again, let's clear all this. We could do something like this. Let's start from 0, start from 4, and make this -4. If you run this thing, right, what I'm going to do now is I'm going to change the acceleration to +4 and run this again. All right, and now I could change this back to -4. And so what I'm showing you now is you could actually take a constant acceleration problem and split it into sections. And so these are called piecewise functions, right? And so you could actually make almost any function you want by changing these things in stages. We could discuss this more in task 3 in the lab this week, or if you're curious, you could literally do a bunch of different little constant acceleration problems to figure this out. You could do a constant acceleration problem for the first 2 seconds, start the clock over and do another constant acceleration here, start the clock over, do it again. And the idea is during this stage, acceleration should be -4. Oh, and let me, there we go. That way you could see it a little bit better. The idea is you could just do separate problems using your constant acceleration kinematics and approximate an oscillation this way if you wanted to. All right. Any questions about that while I have this up here? Just kind of fun to see it. So you're not falling asleep. Why don't you try and figure out a spot on this graph where it's moving forwards and slowing down. Where would that be? Think of a time when it's moving forwards and slowing down. And you could just think to yourself, you could answer in the chat, you could unmute, whatever you want. But I'm looking for a time when it's moving forwards and slowing down.
By forward, you mean moving to the right?
That's right. So when I say moving forwards for an X problem, meaning it's moving in what I would mean moving to the right. Okay. Yep.
6 to 8 because of school.
So it'd be the first quadrant and the third quadrant?
They said, yeah, you know, by
It's like,
okay.
0 to 2 seconds, and then 4 to 6 seconds.
So I heard 4 to 6 seconds. Let's check that out. So
You said slowing down, right?
moving forwards and slowing down.
Yeah.
4 to 5 seconds.
So I heard. Okay.
Oh,
Sorry.
so yeah, that's right. Yep.
She said, okay, that's fine. You know,
Okay.
we'll wait.
I'm getting distracted by the
So
sound in
next
the
thing I get a
background.
text,
Could
"Hey,
you?
I need you to fill out.
Thanks. Yeah. Sorry. And I understand we all have complicated lives right now. So I just had to think there. So somebody said, I don't remember who said it, but someone said before 4 and 5 seconds. So let's take a look. Here it is. Let's see. Velocity's positive. Here, acceleration is negative. Absolutely. That's moving forwards and slowing down. All right. How about when is it moving? So somebody else other than those two, I think that was Jacob and Esteban, somebody other than those two, let's try and think of a point in time when it's moving backwards and slowing down.
Between seconds 2 and 3.
Let's see, 2 and 3. So 2 and 3, velocity is negative. That means moving backwards or moving to the left. A is positive. Absolutely. So this would be a time it's moving left and slowing. And so if you can start to do this, are there any times where this thing is at rest? Somebody else that hasn't answered. What times are this, will we say this object is instantaneously at rest? Give me one time.
1 second.
1 second. Whenever velocity is 0, this thing is at rest. So notice this graph is actually really useful. In practice, this graph is what is easy to get from a video. If you videotape something, or not video, maybe you make a video with your phone. That tells you my age. I think of videotaping, but whatever. It's very easy for us to analyze the motion of a video by studying something's position versus time. Then we're going to do a process called numerical differentiation to figure out these two plots. We're going to learn that in lab this week, then apply it in weeks 3 through 5. So we're going to deal with this over and over and over again. So you want to be really good with graphs. I don't know. It's just my philosophy is students need to understand graphs inside and out. All right. Good job there. Any questions? All right. I want to point out something in the workbook that might help you lock this down. Excuse me. All right. So there's lots of problems here. Here's an easy one to get you started. This one, you could just follow along with it. All right. And if it helps, these are like some ways you could compare these things. You can see that I'm asking the same kind of question. Here's one very similar to what we just did, where notice the acceleration changes over the different stages. All right. This handout or whatever, forget that. That's just what I just showed you, the moving man. We just did it. All right. This problem is really good. All right. So I'm going to look at question 2.28 really quick, just to remind you of something. All right. So let's say I want to get the velocity at this point. Take a second to read the problem and think to yourself, don't unmute here. Let's let everybody think. Let's say I want to get the velocity at 4 seconds. So think to yourself, or you could send a private chat message to anybody you want if you have a partner in the class that you work with, or you could text them if you're into that or whatever. But yeah, just basically don't blurt it out. I want to get the velocity at 4 seconds. Oops. So think through what you would do. You don't have to do it. Just think how you would do it. Okay. So a lot of students, I find, end up taking this point, and they do a slope like this. And they try and get the slope there. And they say, aha, the slope is negative. That's a very good first attempt, but it's wrong. That is, let me show you why by showing you the solutions. 2.28. Oops. Okay, here's the idea. If you look at this, sorry I used red and green. This red slope, or this slope right here, is way off from the realistic value. The idea here is you want to use points close to the point of interest as possible. You do not want to go way off up or below. Notice that if you do that, you're off by 40%. That's terrible. So you want to pick points just before and just after anytime you need to get the slope. Okay. So going back to here, I'm going to walk you through this problem. This is what I'm thinking. Okay. We know the first thing I do is I notice I've got an XT plot. So what do? When I have an XT plot, I go to my workbook. Whoops. And what page was that chart on? I think it was 30 something, 31. I go to here and I say, okay, the first thing I do is if I'm dealing with an XT plot, I make sure I read the XT rules. You would be surprised how many students accidentally do the VT rules on an XT plot. So make sure you know when you're doing an XT plot, you read the XT rules. That says, oh, slope relates to velocity. So I go back into there. I say, okay, once you identify the type of plot as XT, come on. Why is it not? There we go. Once I identify this as an XT plot, I know that slope equals velocity. And that is what gets me rolling. So then moving to the right, that says velocity is positive. So I'm looking for all times slope is positive. So that's right here, right here, right here, right here, and maybe right over here as well. So that's how you get these time intervals. How do I get the velocity at this one particular time? I could use some points close to it. And why not pick some points that lines up on one of the grid lines? It could either line up on the horizontal grid lines or the vertical. Okay. And then you're off to the races and you can do the rest of this stuff. This is the kind of stuff we were just doing. Questions on that? It's a really good problem right there. Make sure you do it. I don't know if I asked that to be written up, but you got to at least do that so you understand it. Let's go back to the next one. Look at this one. Xikra and Vega, if you're wondering, that's what I wanted to name my children, but didn't work out. I got vetoed. Anyways, probably good for them, huh? Now, this problem, what's the first thing I'm going to ask you to look for, do you think? Before we do anything, what's something you should make note of?
That it's a VT curve.
Yeah, the type of
Or
plot.
VT plot.
Yeah, we've got a VT plot. So then I go say, hey, this type of plot is VT. So I'm going to think about the VT rules and not accidentally use XT. And so now I know, aha, area means displacement or change in position. And then also I know that the slope is acceleration. So now the rules are different, or basically the slope and the areas have different meanings. Going back into there, then we're going to read this stuff. Okay, if I want the acceleration, that's the slope. If I want instance when Vega is at rest on a VT plot, at rest is the value of V. So where it intersects. Notice this is very different than up above. Up here, if I wanted to find times where it's at rest on this one would be V equals slope equals 0. So here, this would be at rest, this would be at rest, and this would be at rest. Notice the same question requires different interpretations depending on the type of plot. If you have an XT plot, you follow one set of rules. The slope is velocity. If you're doing a VT plot, if you're doing a VT plot, velocity is just the values. So whenever it crosses the axis. So for this one, right here corresponds to at rest. The slope would be the acceleration, et cetera, et cetera, et cetera. All right. Yeah. So this is a crash course on how to read these plots, and you're not going to get it unless you do lots of practice problems. We've got about 10 minutes left. I'll show you something crazy here just for fun. You might be saying, geez, this is just a bunch of math. And it really is a bunch of math right now. But if I go to here, let's try 2.50. Okay, let me see. Is this the one I want? Yeah. If you're curious, these problems, I think it's 2.50 through 2.53, kind of put them all together. Notice here we have an acceleration, which requires separation of variables. And then you could do all this stuff. And so if you're really crazy and want to really get far into this, that's what these questions are about. And notice this is where the physics actually gets involved. So, and some of you may end up doing this for a lab in weeks 3 through 5. Here's a different one. What if you wanted to understand an acceleration here like this, right? And in this case, this is a plot of position versus time. So I'm trying to understand that. And so here would be an acceleration for that. And you could understand that with the graphs, et cetera. And you might have to do some derivatives, and there's some numbers. Similarly, this would be for high-speed drag. So the marble through corn. So if you're curious, all the physics is in there. Great. Those problems are really cool, but yeah, whatever. All right. What did we get hopefully today? All right. Let's remind ourselves what we tried to learn today, and it won't sink in until you do lots of problems. All right. So hopefully what you've learned is this. Okay. And if we're going the other way, we learned there's a little catch here. Glare. Whatever. All right. Let me see if I can get rid of some of that glare over here. Hold on. Where's my mouse? There we go. That didn't help that much. All right. So we know that this is a relationship. This is called instantaneous velocity and instantaneous acceleration. So that's the velocity. Whoops, sorry. That's the velocity at any one instant. This is the acceleration at any one instant. We know that vectors are implied, but we never write them. So positive values usually mean to the right or up. Negative values would mean to the left or down. Obviously, if we used a Y here, that'd mean up and down instead of right, left. Okay. We know that you could use integration and derivatives. By that, I mean, if you start with position, you could take a derivative to get velocity, a second derivative to get to acceleration. Or if you start with acceleration, you could do integration and integration. We watched out for separation of variables. We said that would be an extra credit question possibly on the test. So we know that you can do separation of variables. We will use it in another class, but it is not required for a regular test question, only extra credit possibly. And then another thing that we talked about today was the graphical equivalence. In particular, slopes and areas. We know, we know that a derivative is equivalent to a slope and an integral is equivalent to an area. And we said the biggest thing we have to watch out for is when you integrate, the area is not velocity, it's change in velocity. When you integrate again, the area is not position, but change in position. So those are some things we got to watch out for. And then next time, what I'm going to do is we're going to do a whole bunch of word problems with this and analyze that. Oh my gosh, I think that's a good spot to stop. Any questions? Intense, right? Okay. Practice, practice, practice. And like I said, there's going to be a group activity at the end of Wednesday relating to this stuff. So those of you that were whining about needing more time, you better do some homework. All right. So yeah, the next one, the gloves are off and I might actually just grade it. And yeah, so now keep in mind, if you guys work hard and try, you'll probably get most of the points, regardless of how crappy you are and how little you get done. But yeah, like you might get half of the points just for turning in something, and then I'll grade the rest of it prorated how far you get in the task. So if you want to get all the points for the group activity and improve your chances, you should actually read and practice a little bit before, and I think it'll be pretty easy. Well, I should be careful. Might not be easy for you because you're still learning it, right? All right.